Welcome to the new era of video creation with Bayozi. This is our new series on teaching deep learning. Today, we will discuss the depth estimate and stereo vision. Here are the contents. Depth estimation is an essential task in computer vision, aiming to estimate the distance of objects within a scene relative to a camera. Depth is crucial in tasks such as 3D reconstruction, robotics, and autonomous driving, where understanding the geometry of a scene is necessary for navigation and interaction. One of the most widely used methods for depth estimation is stereo vision, which uses two or more cameras to capture the scene from different angles. By comparing the images from the cameras, the system can calculate the depth of objects based on the disparity between the two views. While stereo vision is popular, other methods such as structured light and monocular depth estimation, which uses a single camera and machine learning techniques, have also gained traction. In this lecture, we will focus primarily on stereo vision and depth estimation, exploring how these techniques work and their applications. Stereo vision is inspired by human binocular vision, where the brain uses the slight difference in views between two eyes to infer depth. In stereo vision, two cameras are placed at different viewpoints, and each camera captures an image of the same scene. The difference in the image locations of corresponding points is known as disparity, and it is inversely proportional to the depth of the object. To compute depth from stereo images, the key principle is that the greater the disparity between the two images, the closer the object is to the cameras. Conversely, objects that appear more similar in the two images are farther away. To perform this calculation accurately, camera calibration is crucial. The cameras need to be calibrated to ensure that their relative positions and orientations are known. This allows for an accurate measurement of disparity and depth, enabling 3D reconstruction from stereo image pairs. At the heart of stereo vision lies epipolar geometry, which describes the geometric relationship between points in two images. When we know the position of a point in one image, its corresponding point in the other image must lie on a specific line, known as the epipolar line. This reduces the search space for matching points and simplifies the problem of finding corresponding points between the two images. Stereo camera calibration involves determining the camera parameters, including the focal length and the relative position and orientation of the cameras. This is essential to ensure that the disparity calculations are accurate. The fundamental matrix and essential matrix are used to describe the transformation between corresponding points in the two images. In practical stereo vision systems, algorithms use these matrices to rectify the images, ensuring that the epipolar lines are aligned horizontally. Once this is done, finding corresponding points becomes a one-dimensional search along the epipolar lines, making the stereo matching process more efficient. Once the stereo images are rectified, the next step is stereo matching, where we find corresponding pixels, or image patches, in both images. The goal is to identify which points in one image match with points in the other image. A basic technique for stereo matching is block matching, where small patches around a pixel are compared between the two images. The block with the best match indicates the corresponding pixel in the second image. However, block matching can be prone to errors, especially in areas with low texture or repetitive patterns. More advanced algorithms like semi-global matching, SGM, address this by considering the global structure of the image and minimizing matching errors over large regions. Additionally, optimization techniques like graph cuts and dynamic programming are used to refine the matching process, improving the accuracy of depth estimation by reducing mismatches. These techniques allow for robust depth estimation even in challenging scenarios, such as regions with low texture or occlusions. The output of stereo vision is typically a depth map, which represents the estimated distance of each pixel from the camera. This map is computed using the disparity between corresponding pixels in the two stereo images. The relationship between disparity and depth is given by the equation depth, baseline x focal, length disparity, text sarge depth, yarendien frak bach r text, baseline in times, r text, focal length, a text, disparity, where the baseline is the distance between the two cameras and the focal length is the intrinsic parameter of the camera. The disparity map generated by stereo matching contains the horizontal pixel shifts between the two images. After obtaining the disparity map, a depth map is created. However, raw depth maps can contain noise, especially in regions with low texture or occlusion. To improve the quality of the depth map, post-processing steps like smoothing and filtering are applied. For stereo vision systems to accurately estimate depth, proper camera calibration is essential. Camera calibration involves estimating both intrinsic and extrinsic parameters of the cameras. Intrinsic parameters include the focal length, principal point, the center of the image, and distortion coefficients that account for lens distortion. These parameters describe how a 3D point is projected onto a 2D image. Extrinsic parameters define the relative position and orientation of the cameras. This includes the rotation and translation between the two cameras, which is crucial for establishing the geometry of the stereo setup. The calibration process often uses a checkerboard pattern or other known patterns in a series of images to estimate these parameters. Once calibrated, the stereo system can compute the disparity in depth with greater accuracy. Despite its effectiveness, stereo vision comes with several challenges. Occlusions. In some parts of the scene, one camera may not be able to see an object that the other camera can. These occlusions lead to errors in depth estimation, as there is no corresponding point in the second image to match. Textureless regions. Matching becomes challenging in areas where there is little texture or distinct features to track. Homogeneous regions, like large walls or empty spaces, often result in incorrect matches. Disparity refinement. The raw disparity map generated by stereo matching may contain noise, particularly in occluded or textureless areas. Post-processing steps like filtering and refinement are necessary to improve the depth map. Real-time processing. Stereo vision requires significant computational resources, especially when operating in real-time systems, like autonomous driving or robotic navigation. Optimizing algorithms for speed while maintaining accuracy remains a challenge. In structured light depth estimation, a known pattern, such as stripes or grids, is projected onto the scene, and the deformation of this pattern when viewed by a camera is used to infer depth. The change in the pattern's appearance allows the system to estimate the 3D shape of the objects in the scene. Structured light systems, such as the Microsoft Kinect, use this technique to generate depth maps quickly. They are particularly accurate in controlled environments where lighting and the pattern projection can be carefully managed. However, structured light systems can struggle in outdoor or unstructured environments due to changes in lighting conditions or occlusions. Monocular depth estimation refers to estimating depth using a single camera, a challenging task since no disparity information is available. Instead, monocular depth estimation relies on machine learning models, particularly convolutional neural networks, CNNs, to predict depth from a single image. These models are typically trained on large datasets of images with ground truth depth maps, enabling the system to infer depth from the visual cues in the image, such as object size, texture, and perspective. While monocular depth estimation is less accurate than stereo vision, it has the advantage of requiring only a single camera, making it ideal for mobile applications and augmented reality, AR. Depth estimation plays a vital role in many modern applications. 3D reconstruction. Depth estimation is fundamental for converting 2D images into 3D models, a process used in fields like architecture, virtual reality, and cultural heritage preservation. Autonomous vehicles. Depth maps allow autonomous vehicles to detect obstacles and navigate in 3D environments. Accurate depth estimation is crucial for safety and navigation in self-driving cars. Robotics. Robots rely on depth estimation for navigation and manipulation, such as when picking up objects or avoiding obstacles. Depth maps enable precise control in complex environments. Augmented reality. AR systems require depth information to correctly overlay digital objects on top of the real world. Depth estimation allows AR applications to provide more realistic and immersive experiences. Achieving real-time depth estimation through stereo vision is a significant challenge. Stereo matching and depth calculation are computationally expensive tasks, often requiring specialized hardware or optimized algorithms for low-latency processing. GPU acceleration is commonly used to speed up stereo vision algorithms by leveraging the parallel processing power of GPUs. Real-time stereo vision is crucial for applications like autonomous driving, where depth maps need to be generated in real time for obstacle detection and navigation. Optimizing algorithms to balance performance and accuracy while ensuring fast processing is an ongoing area of research in computer vision. In many practical applications, especially autonomous driving, hybrid approaches that combine stereo vision with other sensors, such as LiDAR or radar, provide more accurate and robust depth information. Stereo vision may struggle in certain conditions, such as low light or weather-related occlusions. By combining multiple sensors, these hybrid systems can compensate for the weaknesses of individual sensors. For example, LiDAR provides highly accurate distance measurements, but lacks the resolution and detail of visual data. By fusing depth maps from stereo vision with LiDAR data, the system can create more accurate 3D models of the environment. In many practical applications, especially autonomous driving, hybrid approaches that combine stereo vision with other sensors, such as LiDAR or radar, provide more accurate and robust depth information. Stereo vision may struggle in certain conditions, such as low light or weather-related occlusions. By combining multiple sensors, these hybrid systems can compensate for the weaknesses of individual sensors. For example, LiDAR provides highly accurate distance measurements, but lacks the resolution and detail of visual data. By fusing depth maps from stereo vision with LiDAR data, the system can create more accurate 3D models of the environment. The future of depth estimation lies in improving accuracy and efficiency across various methods. With the continued advancement of deep learning, we expect even more accurate monocular depth estimation techniques, reducing reliance on expensive stereo or multi-sensor setups. AI integration will enable dynamic scene understanding, allowing systems to infer depth and context simultaneously, adapting to changing environments. Additionally, there will likely be continued improvements in creating low-cost, efficient stereo systems that can be integrated into mobile devices or consumer electronics. Finally, we will see better fusion techniques for combining stereo vision with other sensors, providing more robust depth information and improving real-time performance in complex environments. In conclusion, depth estimation is a cornerstone of modern computer vision, enabling 3D reconstruction, autonomous navigation, and more. Stereo vision is a powerful technique, but it has limitations, particularly in occlusions, textureless areas, and real-time performance. Monocular depth estimation and hybrid approaches offer exciting alternatives that are more suitable for resource-constrained environments or real-time applications. As technology progresses, improvements in deep learning, sensor fusion, and real-time processing will lead to even more accurate and efficient depth estimation systems, driving advancements in fields ranging from robotics to augmented reality. Thank you for your attention. Now, I'd like to open the floor for any questions or discussion. Feel free to ask about any specific applications, challenges, or research areas in depth estimation and stereo vision. We can also delve deeper into how deep learning is being applied to improve these techniques, or talk about the ongoing research in real-time systems.